NENOMATICA, where mathematics meets YouTube excellence. In this video, we'll learn how to expand the square of a sum with multiple terms. This is a fundamental algebraic identity that generalizes the familiar binomial expansion. Let's begin by looking at the general form of this identity. If we have the sum of n terms, a_1 plus a_2 plus a_, and we square this expression, we'll get a specific pattern. The formula we'll derive is the square of the sum equals the sum of the squares of all terms plus twice the sum of all possible products of distinct terms. Let's derive this formula step by step. First, we'll write the square as a product of two identical sums. This is simply a_1 plus a_2 plus a_n multiplied by the same expression again, a_1 plus a_2 plus a_n. Next, we'll use the distributive property to multiply each term in the first factor by the entire second factor. This gives us a_1 times the entire second sum plus a_2 times the entire second sum, and so on up to a_ times the entire second sum. Now, let's group the resulting terms. When we multiply through, each term a_i gets multiplied by itself, giving a_i squared, and also gets multiplied by every other term, giving products like a_ times a_j. First, let's collect all the square terms, a_1 squared, a_2 squared, and so on up to a_n squared. Then, we have all the cross products. Each pair of distinct terms a_i and a_j appears twice, once when a_i multiplies a_j, and once when a_j multiplies a_i. Finally, we can write this more compactly using summation notation. The square terms can be written as the sum of a_i squared, where I runs from 1 to n. The cross products can be written as twice the sum of a_i times a_j, where I is less than j _i squared, where I runs from 1 to n. The cross products can be written as twice the sum of a_i times a_j, where I is less than j to ensure we only count each pair once. This gives us our final formula. Let's see how this formula works with a concrete example. Consider the case of three terms, x plus y plus c squared. Applying our formula, we get the sum of the squares x squared plus y squared plus c squared, plus twice the sum of all possible products, 2 times x times y plus x times z plus y times c. This simplifies to x squared plus y squared plus z squared plus 2xy plus 2xc plus 2yz. We can also visualize this expansion geometrically. Let's consider the case with two terms. Here, our terms are 2x, 3y, and z. First, we find the sum of squares, 2x squared plus 3y squared plus c squared, which gives us 4x squared plus 9y squared plus c squared. Next, we calculate twice the sum of all possible products, 2 times 2x, 3y plus 2x, z plus 3y, z, which simplifies to 2 times 6xy plus 2xc plus 3yz, or 12xy plus 4xc plus 6yz. Putting it all together, our final answer is 4x squared plus 9y squared plus z squared plus 12xy plus 4xc plus 6yz. Find the expansion of x plus y plus z plus w squared. Take a moment to think about how you would apply our formula. Using our formula, we get x squared plus y squared plus z squared plus w squared, plus 2 times xy plus xc plus xw plus yz plus yw plus cw. Let's summarize what we've learned. The square of a sum of n terms equals the sum of the squares of all terms, plus twice the sum of all possible products of distinct terms. This formula is extremely useful in algebraic manipulations, especially when expanding complex expressions. For practice, try expanding expressions like a plus b plus c plus d squared, or p plus q plus r plus s plus t squared on your own. Understanding this generalization of the square of a sum allows us to expand complex expressions efficiently. The pattern is always the same. Sum of squares plus twice the sum of all possible products. Expressions efficiently. Let's look at our example. We need to expand the expression to a cubed minus 3a squared plus a minus 4, all squared. Let's begin by carefully rewriting this expression. For step 1, we need to recognize that our expression contains 4 terms, but we can rewrite it as a trinomial by grouping the first 3 terms together. This makes it easier to apply the trinomial square formula. For step 2, we'll apply the formula for the square of a trinomial. The general formula states that the square of a trinomial is equal to the square of the first term, plus the square of the second term, plus the square of the third term, plus twice the product of the first and second terms, plus twice the product of the first and third terms, plus twice the product of the second and third terms. So applying this formula to our expression, we get the square of 2a cubed plus the square of negative 3a squared, plus the square of a minus 4, plus twice the product of 2a cubed and negative 3a squared, plus twice the product of 2a cubed and a minus 4, plus twice the product of negative 3a squared and a minus 4. For step 3, let's expand each of these terms. The square of 2a cubed gives us 4a to the 6th power. The square of negative 3a squared gives us 9a to the 4th power. For the square of a minus 4, we use the square of binomial formula, where the square of a plus b equals a squared plus 2ab plus b squared. So the square of a minus 4 becomes a squared minus 8a plus 16. Next, twice the product of 2a cubed and negative 3a squared gives us negative 12a to the 5th power. Then, twice the product of 2a cubed and a minus 4. This expands to 4a to the 4th power minus 16a cubed. Finally, twice the product of negative 3a squared and a minus 4. This expands to negative 6a cubed plus 24a squared. For step 4, let's combine all like terms to simplify our expression. We'll combine all the terms with the same power of a. For a to the 6th power, we have 4a to the 6th. For a to the 5th power, we have negative 12a to the 5th. For a to the 4th power, we have 9a to the 4th plus 4a to the 4th, which gives us 13a to the 4th. For a cubed, we have negative 16a cubed plus negative 6a cubed, which gives us negative 22a cubed. For a squared, we have a squared plus 24a squared, which gives us 25a squared. For a to the 1st power, we have negative 8a, and for the constant term, we have 16. So our final answer is 4a to the 6th power minus 12a to the 5th plus 13a to the 4th minus 22a cubed plus 25a squared minus 8a plus 16. This is the expanded form of our original expression, 2a cubed minus 3a squared plus a minus 4, all squared. Let's summarize what we've learned. First, we recognized how to rewrite our expression to make it easier to apply the square of a trinomial formula. Then, we applied the formula and expanded each term carefully. Finally, we combined like terms to get our final answer. This technique can be applied to expand other complex expressions as well. Welcome to this video on expanding the square of a multinomial. Today, we'll be looking at how to expand the expression a plus b plus c plus d plus e squared. When we square a multinomial, we're essentially multiplying the expression by itself. To expand this properly, we need to understand what happens when we multiply these 5 terms by themselves. When expanding this expression, we need to use a specific rule. The square of a multinomial equals the sum of the squares of each term, plus twice the product of each pair of terms. Now, let's break this down step by step. The first step is to identify all the terms we have. In this case, we have 5 terms, a, b, c, d, and e. The second step is to use the general formula for expanding the square of a sum of 5 terms. We can express this as u plus v plus w plus x plus y squared equals u squared plus v squared plus w squared plus x squared plus y squared plus 2 times the sum of all possible products, u times v, u times w, u times x, u times y, v times w, v times x, v times y, w times x, w times y, and x times y. The third step is to substitute our original variables back into the formula. So, replacing u with a, v with b, w with c, x with d, and y with e, we get a plus b plus c plus d plus e squared equals a squared plus b squared plus c squared plus d squared plus e squared plus 2 times a times b plus a times c plus a times d plus a times e plus b times c plus b times d plus b times e plus c times d plus c times e plus d times e. The fourth and final step is to distribute the factor of 2. The fourth and final step is to distribute the factor of 2 over all the pairwise products. Now, let's visualize this pattern more clearly. Notice that we're squaring each individual term, and then adding twice the product of each possible pair of terms. This creates a systematic pattern where each term is multiplied with every other term exactly once, and the result is doubled. Let's take a moment to count the number of terms in our final expansion. We have 5. Let's take a moment to count the number of terms in our final expansion. We have 5 squared terms, 1 for each variable, and we have 10 product terms, each multiplied by 2. In general, when expanding a plus a2 plus superscript 2, we'll have n squared terms and n1/2 product terms, each multiplied by 2. Let's summarize what we've learned. When expanding the square of a multinomial like a plus b plus c plus d plus e squared, we follow this pattern. We square each individual term, then add twice the product of each pair of terms. The final answer is a squared plus b squared plus c squared plus d squared plus e squared plus 2ab plus 2ac plus 2ad plus 2ae plus 2bc plus 2bd plus 2be plus 2cd plus 2ce plus 2de. Sparkles note, this pattern extends to any number of terms. As a challenge, try expanding a plus b plus c squared on your own using the same method we've used today. Remember to square each term and include twice the product of each pair of terms. Slide in, let me show you a useful memory aid for this formula. Think of it as filling a grid where each cell represents a product of terms. Let me show you a useful memory aid for this formula. Think of it as filling a grid where each cell represents a product of terms. The diagonal represents the squared terms, and the off-diagonal elements represent the cross-product terms that get doubled. To complete our explanation, I want to emphasize that this pattern works for any number of terms. The general formula for the square of a sum with n terms is the sum of the squares of each term, plus twice the sum of all possible products taken 2 at a time. This type of expansion helps us understand algebraic manipulation and is often used in polynomial operations. Before we start the actual expansion, let's recall the general formula for squaring a sum of terms. When we have the square of a sum, it equals the sum of the squares of each term plus twice the product of each pair of terms. For example, with 2 terms, we have the famous formula. A plus b squared equals a squared plus 2 times a times b plus b squared. But for our problem with 4 terms, we'll need to square each term and add twice the product of every possible pair of terms. This will give us a lot more cross-product terms. Let's start by identifying the 4 terms in our expression. We have a cubed as our first term, a squared as our second term, negative a as our third term, and negative 1 as our fourth term. Let's start by calculating the squares of each term. First, we square each term. A cubed squared equals a to the 6th power, a squared squared equals a to the 4th power, negative a squared equals a squared, and negative 1 squared equals positive 1. So the sum of all squared terms is a to the 6th plus a to the 4th plus a squared plus 1. Now we need to find all the cross terms, which are twice the product of each pair of terms. With 4 terms, we have 6 different pairs that we need to multiply, and then multiply each product by 2. Let's identify these pairs systematically. Let's calculate each of these cross terms one by one. First, 2 times a cubed times a squared equals 2a to the 5th power. Next, 2 times a cubed times negative a equals negative 2a to the 4th power. Then, 2 times a cubed times negative 1 equals negative 2 a cubed. 2 times a squared times negative a equals negative 2 a cubed. 2 times a squared cubed. 2 times a squared times negative 1 equals negative 2 a squared. Finally, 2 times negative a times negative 1 equals positive 2a. So all of our cross terms are 2a to the 5th minus 2a to the 4th minus 2 a cubed minus 2 a cubed minus 2 a squared plus 2a. Now we can combine our squared terms with our cross terms to get the complete expansion. We have a to the 6th plus a to the 4th plus a squared plus 1, plus 2a to the 5th minus 2a to the 4th minus 2 a cubed minus 2 a cubed minus 2 a squared plus 2a. Let's combine like terms. A to the 6th stays as is. 2a to the 5th stays as is. A to the 4th minus 2a to the 4th gives us negative a to the 4th. We have negative 2 a cubed minus 2 a cubed, which gives us negative 4 a cubed. A squared minus 2 a squared gives us negative a squared. 2a stays as is, and 1 stays as is. So our final answer is a to the 6th plus 2a to the 5th minus a to the 4th minus 4 a cubed minus a squared plus 2 a plus 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.